we'll start our recording. We've briefly looked at the reactivity of each of these three functional groups. In the old format style, this was a super useful summary slide. In the new format, since we're looking at mechanisms, a little bit less useful, but it does at least cover some of the bases. Okay? Our alkanes, just carbons and hydrogens, which means their intermolecular forces are London dispersion. That means weak forces, which means low melting points, low boiling points. If we're trying to get into their reactivity, well, they're nonpolar covalent bonds. They're the strongest bonds we have access to, okay? Which then means they're very difficult to react. And for the most part, the only way we can get them to react is with radical reactions, which we'll see probably week 16, because for the sake of being recorded, not the most popular reactions, not the most useful. Right? Typically, we're looking at some other higher order functional group before we start dealing with radical reactions. Our alkyl halides, because we now have a weaker bond, okay, in the polar covalent bond, we have stronger intermolecular forces, which increases the melting point and boiling point, and it gives us access to polar chemistry, and that's where we have the electrophilic carbon. Okay? It doesn't have to be an alkyl halide. We had alcohols. As soon as we attach an electronegative element to our structure, that changes the dynamics. Okay? And we saw that with the substitution when we had oxygen instead of halogens. Okay? And that's one of the things that's nice about our textbook is we focus on the mechanistic detail, not on the functional group itself. That said, the next section we're moving into is the electrophilic addition. And the electrophilic additions almost exclusively fall on alkenes. Okay? They are going to be London dispersion forces, but they're going to be a slightly stronger London dispersion force than the alkane. Why might they be a slightly stronger force?
Because
the hybridization makes it more electronegative. You've got the electron cloud, okay, of your pi system up above and below, which makes them a little bit more polarizable, so they get a little bit stronger intermolecular forces. They are very heavily structure dependent on cis versus trans. So if you've heard talk about trans fatty acids are bad for you and cis fatty acids are better, okay, it's because the cis are bent. Well, if they're bent, that makes it more difficult for them to crystallize, which then means they stay liquid. Okay, so it's a little bit easier for our body to process. The trans fatty acids are now nice and easily linear, can stack, and we get higher melting points out of them. When we look at our alkene, we're really going to address two big categories on our alkene. We have a nucleophilic carbon, or we have a Bronsted-Lowry basic carbon. In both cases, what is happening? Where is that chemistry coming from? And don't tell me carbon. Carbon doesn't count. The pi bond. Right? The pi bond is our source of electrons. Where those electrons go, if they're being shared with, say, a hydrogen, then we're looking at a Bronsted-Lowry basic pi bond or carbon. If the electrons go to something other than hydrogen, we're looking at a nucleophilic carbon. All right, I like the pen anyway. We also have degrees of unsaturation. There's a little formula down there, which we saw when we looked at mass spec, and I have still yet to memorize. We also have to worry about cis-trans isomerism, which in theory we already remember. Opposite sides, cis-trans, easy, all that fun stuff. Okay, nomenclature, go back and review it if you haven't done so already. Okay, you need to know what's going on with how to name your alkenes, how to apply them, where to find all those pieces, which then takes us to our first little practice. Go ahead and name. Okay, you guys have less people over here. Which side do you guys want to do? The right two or the left two? Okay. This side of the classroom is doing the left two. You guys are doing the right two. Go through, come up with a name as best you can. But now that I'm recording, I have it perfect. So it has to be a cyclohept. Okay? We have a methyl group outside of it, and then we have to decide how we number our ring structure. Okay? Which is a higher priority, the alkene or the alkane? The ene. So the alkene needs to get the lowest number when we're looking at numbering our chain. When we number, we will by definition include both atoms of the alkene at our lowest number positions. So we have to number it 1, 2, like I've got shown clockwise, which makes it a 3-methyl cyclohept 1-ene. Because by definition the alkene is located at position 1, you'll sometimes see it abbreviated cycloheptene. Right, and they'll ignore the 1. It's not technically correct, it's accepted.
So this is your...
This is correct. Okay. Far right, we go through and circle the longest carbon chain. Okay, and this is where that whole methyl argument came up with a little bit earlier ago. Okay. Once we circled the atoms of this, just a second. Once we circle the atoms of the main chain, there are no substituents. That's not a methyl group at either end of that. Those are part of the main chain. So they get folded into the name. There are now 6 carbons. I've got double bonds at positions 2 and 4. So I can call that hex 2,4-diene.
Would you use E like a trans?
Say that again?
Would you put an E at the beginning for trans? Because the bonds are...
So there's an interesting question. Jen's asking about cis and trans. Do we need to worry about cis and trans?
Technically, yes.
Yes, you do. Okay, so we would have to go through and define what the double bond was located. Is it cis or trans? So let's take a look at, say, let's call it the purple one. This purple one is what? Cis or trans?
Trans.
It's trans, and it's trans because we take a look at our larger groups are on opposite sides of the double bond. Okay? Trans is technically not a nomenclature system, it's an abbreviation. To be fully correct, we have to label it not trans, but E. If we look at our now green double bond, our higher priority groups are on the same side, so we could call that cis, just like trans. We can't call it trans. Z. They're on the same side. Okay? So we then have to go through and add the EZ moniker into that. Your EZ notation usually shows up at the front of the name. 2E, 4Z, hex 2,4-diene. Okay? The next fun part is which one comes first. Should it have been 2E, 4Z or 2Z, 4E? I don't remember. I really don't. Yeah, I was asking a question. I don't remember. It has to come back to how you list that and which is appropriate, and you have to be careful in that officially. You don't see the level of difficulty like that pop up on the ACS because you're getting into, it might even be on this slide and in the next hidden part of it. It's a sub rule on how it actually gets labeled out. Yeah, it is. It's rule 2.2.3. And it's Z over E, so it's actually backwards right now. Should actually be the other way around. Okay. So, top left, let's do that one because I think that one's easier. We circle our main chain carbons. How many carbons do we have in our main chain? 5, which is a really, really easy mistake to make because a lot of people will skip over that carbon. Okay, so watch out for that. So we have a 5-membered chain with which functional group? Functional group. The ine. So it'll become pent-ine. Okay. Because again, it is at position 1 by definition. Because it is a higher priority functional group, we can oftentimes see the 1 disappear, though it should always be included. And then we have the chloro located where? 5-chloropent 1-ine. Kind of, sort of? Okay. So thank you, Amanda. Let's call attention to the drawing up on the board for circling the main chain. Why did you circle the main chain as you did? I think I heard it. Someone can follow. It's the longest carbon chain. Okay, so for those people watching at home, we're looking at that carbon chain. Okay, that is the longest carbon chain. Does that longest carbon chain include the highest priority functional group? No. The alcohol is the highest priority functional group in this structure, which then means the alcohol must be included in that carbon chain. Okay. The alkene is then the next highest priority, which must be part of it, which then means we're looking at 4 carbons in our longest carbon chain. It's a butte.
Could you take either CH3, CH3? Could you go either way on the 5-carbon chain?
Well, the 5 carbon chains are relevant.
Well, I'm just saying you drew the line with the CH3.
Yeah, and we said that that's bad. We can't do that because that does not include the alcohol as part of the primary chain.
I think it's,
If we had decided to, whoops, come on, pen, erase that, then it doesn't matter because they're identical.
I wasn't confident though.
Thank you.
Never confident in it.
Okay, so it's a butte. What else do we have? This one gets tricky because we have the alcohol and the alkene. So it's going to become butte. Two ene 1 all. And we have to start numbering from here. 3, 4. The next part comes in is what are our substituents. So I think some people see that Cl and think it's a carbon. We don't have a chloro, we have a dichloro with chlorines located at positions 3 and 4. And then what's that other one? 2 names come out of this. Isopropyl, okay, which was located at position 2. Isopropyl is technically a common name and should not show up in the IUPAC nomenclature system. Doesn't mean it doesn't, okay, but it shouldn't be there. So what else could we call it? For those people that remember it, it's methyl ethyl. Okay. Because we look at our substituent, our substituent has a 2-carbon chain that is the longest, and at position 1 of our 2-carbon substituent, there is a 1-carbon substituent. Okay. That can very quickly become confusing because then we don't know what that 2 is referring to. Okay. Is that 2 referring to the methyl or the ethyl?
doesn't matter, right?
It has to be referring to the ethyl. Because what is between the methyl and the ethyl right now? Nothing's written there. We aren't specifying the location. Okay? So it has to, by definition, mean that the 2 is applying to the ethyl and the methyl is a substituent at position 1 of the ethyl. Okay? Which is confusing as all get out, but that's how it works. Okay? Yes?
Do we get the 5-carbon chain on the structure?
You can get to a 5-carbon chain, but it does not include the main substituents, the primary functional groups. You have to include the primary functional groups.
We still can get 5-carbon and include OH.
But not the alkene.
Oh, so we have both.
Both of those are higher priority functional groups. They must be included in the main chain. Okay? Make sense? At least well enough that we can accept it and move on.
So what would the action be? 3,4-dichloro, 2-methyl
3,4-dichloro, 2-methyl-ethyl, bute 2-ene 1-all. Yes.
That sounds like a different
Yes.
So
Exciting.
Up to someone and say that.
You start with this.
We start with the chloro in our substituent list because C comes before E. So we have the 3,4-dichloro, 2-methyl-ethyl, bute 2-ene 1-all.
and the cis trans.
We also have the cis trans, which then means, which substituent do we have? Are we cis or trans? Okay. Let's work through this one. I'm going to erase all the coloring up on our structure. We look at our double bond. We cut it in half, perpendicular to the bond axis, and then decide. Chlorine versus carbon, which has a higher priority? Chlorine. Carbon versus carbon, which has a higher priority?
Next one out.
Carbons are the same, so we then move to oxygen versus carbon. Oxygen has the highest priority. We now cut parallel to the bond axis. The stars are on the same side, which means cis, which then means Z. On the same side. And as stupid as that may sound, it's the only way I'll remember that. So 2Z34-dichloro, 2-methyl-ethyl-but-2-ene-1-all. Okay? So, lower right-hand corner, that's where we, because someone asked, and I was like, oh crap, I have no idea. So I had to go dig it up and look for it. So it's rule 2, subheader 2, subheader 3. Z comes before E.
Which is, that's weird because it shouldn't go with the alphabet.
Quite possibly. The only response I would have to the alphabet kind of response would then be Z and E are responding to, ooh, that's an interesting idea, cis and trans. It might be cis trans coming from that. I was just going to say it's German. But cis trans might be right.
Represents cis though, and Z is like opposite of each other.
Z is, yeah, it's in German.
Yeah.
Z, from the German word, is on the same side.
Okay.
Yeah. Yeah, so it's Z and E come from German. Okay, so there's enough America out there. So now we're moving into the fun part. When we move into our addition reactions, what we'll end up seeing, and you'll see this a lot in second semester as well, you'll see what are known as spider diagrams. We're starting at one central molecule, okay? And in this case, since we're primarily focused on our alkene functionality, okay, or our pi bond, or a nonpolar pi bond, we start at that central structure and we say, well, what can I react with that central structure? If I react it with HX, so going out the top, what does X stand for? Halogen, so HBr. What happens? Well, I add hydrogen and X. Whoops, we made that a Br. Where did the hydrogen go? The other carbon. So we're adding HBr across the pi bond. Okay. Notice that in that diagram I haven't specified wedges and dashes on that product, whereas in some of the other ones we have. Why? Stereochemistry does show up, and it becomes important for some reactions, but not all. Okay. Is that a stereocenter in the top reaction? No, so I don't have to worry about labeling it with wedges and dashes. Okay. But if I pick just a standard alkene, I don't see a specificity. Okay. If I had just made this a cycloalkane, and I thought I was erasing a different part of the structure, I don't see a specificity of where the hydrogen goes versus where the bromine goes. Okay? And they go to very particular locations. Okay? Those locations are our regiochemistry. Okay? You're responsible for that regiochemistry. And these become much more difficult than our substitution and our elimination reactions, because in a substitution and elimination, we're starting with a substrate that has how many reactive sites? 1. The instant we move up to an addition reaction, I now have 2 reactive sites. There are 2 carbons associated with that double bond. Okay? Where the electrons go with respect to those 2 carbons can change the results I get. Okay? So what we're responsible for is the regiochemistry now and the stereochemistry that comes into this. Right? And that's the point of this kind of diagram, is to show it all, so it's now summarized and you can now manipulate from that. Right? Officially, what we're going to try and do is cover all of those reactions and how they work, the mechanistic detail and all that fun stuff. There's so much content built up behind this that it is difficult to get into all of that detail. So you end up seeing approximations come out of it. You'll see some words pop up, Markovnikov and anti-Markovnikov. Right? Markovnikov happens to be an old, dead Russian dude, okay, that did not know electrons existed. And so his theory for what happened in electrophilic addition was based off of looking just at the products. Okay? And he noticed that hydrogens went to particular locations. Okay? Kind of like what Zaitsev did. What did Zaitsev do? Zaitsev was associated with elimination reactions and deciding where our hydrogens were removed from. Markovnikov is effectively the reverse. Okay? So people will go through and just say, well, where did the hydrogens go, and ignore all of the chemistry and memorize, well, that was a Markovnikov type reaction versus an anti-Markovnikov reaction. Well, what is anti-Markovnikov? It's the opposite of whatever the Markovnikov was. Okay? But in that process, we've removed the mechanistic understanding of what's happening within it. Okay? So that's why I object to those terms, but they will show up. And if you go through and look at most of these reactions, you'll start to notice those patterns. It's good to notice those patterns. It's not so good to memorize them. Okay? Know how and why they're coming about. So that on its own, that's what? 10 more reactions? Can't count arrows, but probably ballpark 10. That's not too bad. In what, 3 weeks? But then we have another 6 more. Okay? In those 6 more, we're now looking at oxidation reactions. Because if we look, the end result of each of those arrows is what to the pi bond? What to the carbons of the pi bond? What happened? So when we go from that central structure to this structure here, the carbons moved? No, they didn't move. What happened? Okay, we lost a pi bond. That's why we're doing an addition. What else happened? We shoved oxygens on. In each of these cases, what happened? We've added oxygens. Okay, we've increased the bonds to oxygen. We did oxidation. So these are all classified in our oxidation reactions. Okay? Because they're slightly different in their dynamics of how those things work, our textbook has kind of scattered them all over the place. This is no different than any other textbook because they scatter them all over the place too. Okay? This section on electrophilic additions and kind of these oxidations of our alkenes gets scattered depending on how someone sees it to best fit. Okay? Really what should happen is it should turn into a massive chapter. Okay? Because there isn't really a nice separate section to put it. They should all go into one big place. Right? So we've got these to remember on top of all of our standard additions. Okay? But if we do oxidation, probably do reduction. So we also have the reductions. Right? What I'm trying to do is show these to you now so you can start to associate those reagents with those chemicals and what possible things come out of it. The hope is that we will cover all of these in enough detail that you'll remember the mechanistic detail. Unfortunately, hopes get crushed. Okay? So what you need to start doing is working on memorizing what those things do and how they stack out and work out. Okay? Questions about that? Really isn't as bad as it looks. Okay? So, electrophilic addition reactions. Okay, our textbook refers to these as electrophilic addition. Some of them are more obviously electrophilic than others. Okay? Really what we're focused on is the reactivity of the pi bond. Okay? How does the pi bond react? Okay? Well, the pi bond is a source of electrons. Okay? So as a source, it can share with something. If it shares those electrons with a hydrogen, What did the pi bond act as? A base. What if it shared those electrons with something other than a hydrogen? Then it's acting as a nucleophile. So really I see two big subcategories. We get chapter 11, our pi bond is reacting with acids. We get chapter 12 and 24, our pi bond is reacting with electrophiles. Okay? The same basic chemistry is happening in all of those cases. Notice where the nucleophile goes. Okay? The nucleophile is always going to the center carbon in both these structures. That seems a bit weird. Why would that be? What charge does a nucleophile typically carry? A negative. What does that mean that center carbon is likely to act as? It should be a carbocation or positively charged. Why would, in both cases, that be a positive charge? What do you mean it's more stable? How are you saying the secondary versus primary? It's not allylic. What was that word? Resonance.
Oh my goodness.
Wow. That's not very nice. If we look at resonance structures for the alkene, there's two possible options. The electrons could either go out onto the terminal carbon or they could go back into the middle of the structure. Between those two structures, which one is more likely to form, black or purple? Black, because? And the negative charge is more stable on a primary position because there's less electron repulsion. So we could focus on the negative, okay, which is good. But let's say we were optimists. Let's assume you guys over here are optimists. You instead focus on the positive. Where do we want the positive to be? Because there's more electrons in the center of our structure. So I want the positive charge in the middle. Either way we look at it, either the positive or the negative, we end up with the exact same intermediate resonance structure. It is that resonance structure that drives 90% of the chemistry in electrophilic additions. Sorry, that's a lie. It's 100% of the reactions for our electrophilic additions. Okay? Which is the part that I really like. Remember how we said Markovnikov, anti-Markovnikov? It goes, oh, well, you get these different results. You don't get different results if you understand that we have things called electrons. Markovnikov was 1870. Electrons were 1890. Okay? Didn't know there were electrons. Okay? So a simple adjustment in what the basic structure of elements are, and we can actually start to use energies to predict how our reactions work, not just memorizing. Okay? So, a couple issues with our pi bonds. Okay? They are nonpolar. Okay? The pi orbital is higher in energy, so it is going to be our most reactive, but it's still a nonpolar bond. Okay? Which means we have to kind of force that reagent to work, or force our alkene to react. This is why we have to add, say, acids, because acids supply a very strong partial positive. Okay? So the alkene can react with those. Okay? If we want to see how we might predict those to react, that's where we can look at our resonance. Okay? We end up with two possible resonance options coming out of that. And just like we said with the last one, where do we get our most likely resonance? Blue or red? It's going to be the blue because we have a secondary carbocation, which is more stable than the primary. And we have a primary anion, which is more stable than the secondary. So by looking at those structures and thinking about the resonance, we can predict something about the reactivity. That means when I go through to look at that alkene structure that's drawn up at the top, what I should really be seeing is that structure drawn in blue. And now when I react this with any other molecule, say an acid, where do I expect the hydrogen to go? Well, to the negative one. Why would the negative one pick up the hydrogen? What charge is the hydrogen? Why is it positive? Bromine is electronegative. It can withdraw the electron density. So what we're matching up is opposite charges. It's not a question of this atom must go there. It's looking at the balance of the charges and placing those charges accordingly. Match up your opposite charges, everything works out. Okay? The caveat within that is that how does it happen? Okay? Does that negative charge pick up the hydrogen and then at the exact same time the bromine shares its electron with that positive charge? Okay? Or does it happen in two steps? Okay? The basics of that come down to what are our pieces? What is the bromine doing? What is the most reactive thing? Okay? And trying to keep those. Okay? So to keep in mind with all of these, your alkene is a weak nucleophile. Okay? You must have a strong electrophilic species. And that, at least according to how our textbook is labeling it, can be a strong acid. Okay? So if we look at our basic mechanistic steps, okay, for our pi bonds acting as bases, the pi bond shares its electrons with the hydrogen. That breaks A off. A comes in at a second step to coordinate. So we're running an acid-base step followed by a coordination. Why might we predict that to happen in two steps? What would A likely be? Let's come up with some possible A's. Bromine, chlorine, iodine. What can you tell me about bromide, chloride, and iodide? They're all weak bases, meaning?
Conjugate acid.
Sure, that works. Good answer. They all have strong conjugate acids. By being weak bases, what are they doing? They're holding the negative charge. If they hold the negative charge, are they going to immediately react? No, it's going to have to be a later stage because they're stable enough on their own, they can float off on their own. That means we get it in two reaction steps, not in one. Okay? So by looking at the stability of each of the pieces that come off, we can now predict something about those. And in this case, what we end up finding out is that we do this in two steps and not in one. Okay?
All acid base is two steps, not one. Is that what you're saying?
No. Acid-base is by definition one step. The red is our acid-base step. What happened in the overall reaction? So let's back that out. So our overall reaction is from there to there. Whoops. What happened in our overall reaction? What did we do? We did an addition. Addition of what? H and A. How did I add A? That's now looking at the mechanistic detail. Okay? In that approach, what I would be thinking about is what I'm adding. Okay? So I look at the alkene and I look at the acid. Okay? I like to do a face test. Which one would I be a little bit more concerned about being splashed in my face? Acid. What about the acid makes me nervous? The hydrogen, the positive hydrogen. Why am I not concerned about the bromide or the chloride or the iodide? They were stable. So what I want to do when trying to propagate this reaction is get to the most stable things possible. So what do I have to do? Cancel the H+. So I do it. How do I cancel the H+? I can take the electrons from the pi bond. This then generates, where is it? There it is. A stable negative charge. Okay. That is now stabilized on its own. I don't have to stress about it. So I can just be like, oh, well, now the reaction's done, except what else do I produce? A reactive charged carbocation. How do I formally neutralize that carbocation? Now I have to do the coordination. Okay. So in an electrophilic addition reaction, one mechanistic sequence is to do an acid-base followed by a coordination. Does that answer your question a little bit better? Okay. So Our overall reaction is an addition. We know it's an addition because there's no pi bond. Okay? This can allow me to predict something about what I need to add as a reagent and potentially predict when looking at a product. Okay? The next layer on this is we have to look at the structure and the mechanism of how it happened to predict something about the stereochemistry and our regiochemistry. Okay, the regiochemistry is actually already shown, actually it's not shown up here. The regiochemistry is saying where the hydrogen goes and where the A goes. Okay. Why is the regiochemistry not important here? What do you mean it doesn't matter? H and A are interchangeable because they're both on secondary carbons with no other substitution patterns to them. We have a symmetric alkene. So in the case of a symmetric alkene, I don't have to worry about the regiochemistry because, well, they're identical. What about stereochemistry? Now that I have the mechanism, I can think about the stereochemistry. Did I start with a stereocenter? No. Oh, well, I didn't start with stereochemistry, I don't need to worry about it then, right? Not quite true. Okay. If I start with an achiral molecule, I must end with an achiral product. Is my product achiral? Is A different from CH3? Is CH3 different from the CH2? Is the CH2 different from hydrogen? Do I have a chiral atom? Yes. So in the process of running this reaction, do I have to worry about stereochemistry? Yep, it's showing up. Okay, well, which one do I get? Do I get R or do I get S? Trick question. I get both. Why do I get both? Why do I get two different products? Nope. We're saying A could be wedged or dashed. That means when it reacted with the structure, it either came in from the top or the bottom. Top or the bottom of what? A carbocation. It came in from the top or the bottom of a p orbital. Okay. Both of those attacks are available to it, which then means I have an equal probability of finding the wedged and the dashed position for the A. Okay. Which means when I look at the product, it is indeed achiral because how many products do I have? 2. 50% R, 50% S, I have an achiral product. Okay? Because I formed both. 2 products come out of this. Okay? Is it really only 2 products? What is the difference between those 2 H's? How do you know which 2 H's I'm referring to? I drew an arrow. Okay, those 2 H's are completely identical, no difference whatsoever. One's red, one's black. How do we know one's red and one's black? Because I drew it on there. Could hydrogen also generate a stereocenter if, say, instead of adding hydrogen, I added deuterium? Yeah. Okay. I get a bunch of products when I run an addition reaction. Okay, particularly with the acid-base ones. The acid-base ones tend to be less of a concern because I'm adding hydrogen. And very typically, what is on our carbon structure? Hydrogen, so we don't have to worry about it. Okay? I always have to worry about, or almost always have to worry about, the carbocation position because that almost invariably becomes a stereocenter. The other one sometimes does, sometimes not, depending on our conditions. Alkenes will always produce at least 2 products because of the different dynamics of how the alkene reacts. We're reacting an alkene, To make an alkene, we have 2 carbons. Keep going. Double bond, I would argue pi bond was better. What's the issue with our pi bond? Where are the electrons? Above and below, which means when those electrons react, we can get both possible planes of attack, which means we have to be concerned about how that reaction occurs. Okay? Do you guys want to take a look at that one? See the energy diagram? Or do you think you guys got it? Okay, we'll move on to the more difficult one. What happens with unsymmetric alkenes? Okay, what do you notice is in common with all of these? They all reacted a pi bond. I think I heard that. What did you say, Joey?
They all reacted the least substituted pair.
I'm not sure I understand what that means. Can you elaborate?
They favored tertiary or secondary.
What favored tertiary or secondary? The halide went to the tertiary or secondary position. It went to the more substituted position. Okay? So what you just observed is effectively what Markovnikov observed, except he looked at hydrogen. Where did the hydrogen go?
There were more hydrogens, or the most hydrogens?
Where there were the most hydrogens. Okay? And thank you for that phrasing, because that's exactly what Markovnikov's rule is. The hydrogens go to the position that has the most hydrogens. Okay? Sometimes known as the rich get richer and the poor get poorer. Okay? The carbon that is more hydrogen rich will get more hydrogens. The carbon that is hydrogen deficient gets less hydrogens. Okay? So what we're noticing is in common is where those pieces go. Okay? And that's all Markovnikov had. But because we had the extra benefit of knowing that we have electrons in our structures, what can we say? In each of those cases, when I look at a resonance structure, where does the pi bond best have its electrons located? On the least substituted position, because that generates the most stable anion and the most stable cation. By looking at the energy of our structures, we can predict where the hydrogen goes and where our halogen goes. We don't have to be saying, oh, well, the hydrogen goes to that position because that's what I see most of the time. Okay? Think about the reactivity of these molecules. Okay?
Is it most of the time, or is it always?
It is all of the time following that reactivity. Okay? Where the negative charge on our carbon goes to the least substituted, and our positive charge goes to the most substituted. If we follow Markovnikov's ruling of where the hydrogen adds, we run into exceptions. Because we can move to reagents where we're not adding hydrogen, we're adding hydride. And what's the difference between hydrogen and hydride? Charge. Hydride is negatively charged. So in those cases where we're now reacting hydride, instead of saying, oh, it's reactive because it's a different charge, and now following our charge patterns, we say, oh, well, now it's anti-Markovnikov. Because I don't want to have to understand where the electrons go. I'm just going to stick hydrogens on my structure. You can guess my opinions of those descriptions. Okay? They're not wrong per se, but they're focused less on the how and on the what. Okay? I want you to be thinking about the how. What is important, but the how can get you to answers that you've never seen before. The what leaves you dead in the water if you ever see something that you don't recognize. Okay? So, mechanistic detail. React 1-methyl-cyclohexene with hydrochloric acid. Provide all possible mechanisms and products. Okay. So a good place to start. What is 1-methyl-cyclohexene? It's a cyclohexene. Give me more.
6 in a ring structure.
6 in a ring structure with an ene
And a 1 methyl.
and a 1 methyl. I'm going to react that with
Hydrofluoric acid.
all possible mechanism products. Okay? Because this is now all possible, we'll end up with 2 products. What will those 2 products be? One of those is the correct product based on what we've talked about, on how those charges balance out. One of them is incorrect. Okay? So what we want to do is come up with the mechanisms to show those, and then we'll draw the energy diagram. Because guess what the energy diagram will help us see? Why we would favor one over the other. Right? So see what you can come up with. I'll give you 3 minutes. The double bond, the pi bond. So we're taking electrons out of that pi bond and we're sharing them with the hydrogen. Okay? You might encounter something drawn like that, whoops, where I erased away too much. And sometimes it can be helpful to actually show the bond so that you can actually see the electrons shift a little better. Okay? What's the result of that? Okay? As a hint, I'll give you the easy part. Chloride is a product. Where's the hydrogen attach? The double bond, okay. So the structure I get is this. Okay. The electrons are officially oscillating between both those carbons. Both of those are possibles out of this reaction. So what we would do is show both of those. Which then means the chloride can then come in and react at both of those positions. And we end up with 2 possible products. And what we talked about is said that we might expect one of those to show up in preference to the other one. The red one should show up in preference to the blue one. So, well, why would that be the case? If I compare the red structure to the blue structure, which of those is higher or lower in energy?
The top one's lower.
Why is the top one lower in energy than the bottom one? Most substituted. To be most substituted, that means I'm putting more electrons where? Near something that has a lot of electrons, which would suggest the red one should be higher in energy. Ouch. So that means if we look at our products, the one that we said should form does not form based off of our products. This is potentially why Markovnikov got to attach his name to it. Because if we look at it, we would say red should not form because it's higher in energy than blue. Markovnikov noted that the other one happened. Okay? And what was he missing? Everything in the middle. What does everything in the middle tell us? We have the blue result and we have the red result.
It's easier to get to the red result.
Why is it easier to get to the red result?
Because you form a more stable carbocation.
I form a more stable carbocation, which means it's lower in energy. Which then means the blue product is a slower reaction than the red product, even though the blue product is technically more stable. Okay? How much more stable? Super subtle. Super, super subtle. Okay? But that kind of conditioning is something that can happen, and we will see differentiation come up with some of our reactions. The red product is technically the fastest product. Because it is fastest, we can refer to it as the We talked about speed in 152. We looked at it as,
Rate.
yeah, rate, except begins with a K. Kinetics. Our red one is technically our kinetic product because it has the lower activation barrier. The blue one, being a lower energy product, is the thermodynamic product, because I don't care how I got there, I just care that it's lower in energy. In this particular reaction, the difference between those products is so subtly unimpressive that we end up seeing exclusively the red product. Everything about the red product especially pushes to it. There's no difference in energy between our products, but the red one has a much lower activation barrier. Which step is the slow step? Okay, there's either first or second step.
Second, first.
It is one of those two, yes. No.
First step.
Why the first step?
Because we're forming carbocations.
Okay.
Energy's going up.
Because we're forming a carbocation, our energy increases. If it was the second step, which product would I expect to win out? The blue one would be the primary product. Okay? Because its activation barrier is actually going to be a little bit shorter because it has a larger thermodynamic drop. Okay? So by looking at our energy diagrams, we can predict something about our reactions. We can think about stability and help us process our way through it. Okay? 1870, Markovnikov said the red product mostly formed despite the energy difference. Okay? Really had no explanation for it. The lesson that we really need to be getting out of this is we need to form the most stable products, or the most stable intermediates. Is that always going to be the case? No. Okay? If we end up with a product that is higher in energy for some reason, significantly higher, like involving pi bonds, then we have to worry about it. Okay? If we're all at sigma bonds, they're all roughly the same energy, we aren't going to see a difference. What we're referencing here is what's known as Markovnikov addition. Okay, for those of you that want to remember that name. Wow, that was the same slide. Practice predicting. We got 5 questions here. These 5 questions I will ask again at the start of Wednesday's lecture. It'll be our little quiz, 5 questions. Since you've got 2 days to do them, I'll give you 5 minutes at the beginning of Wednesday's class.